94.7%. That is the number that reportedly stopped a room full of researchers cold, a confidence score, generated not by a historian or an archaeologist, but by an artificial intelligence asked to do something no textbook had ever managed. Explain, from the evidence alone, why the oldest monument on the Giza Plateau doesn't look like it belongs to the age we've been told it belongs to. For nearly 2 centuries, the Great Sphinx has been treated as a settled question. A lion's body, a pharaoh's face, carved on the orders of a 4th dynasty king named Khafre roughly 4,500 years ago. It sits in almost every schoolbook, almost every museum placard, almost every documentary that has ever aired on the subject. But settled questions have a strange habit of reopening themselves the moment someone looks closely enough at the stone, and that is exactly what happened when a wave of new data, gathered from laser scans, seismic surveys, and decades of climate reconstruction, was fed into Grok, the AI system built by Elon Musk's company xAI. What came back wasn't a wild new legend. It was something quieter and, in some ways, more unsettling. A pattern in the rock that the AI said pointed toward an age for the Sphinx far older than anything in the official record. Before we go further, it's worth being honest about what this story is and isn't. It is not a courtroom verdict. It is not a discovery that overturns Egyptology overnight. It's a re-examination of an old and genuinely unresolved scientific debate, run through a new kind of lens, and the debate itself has a real history, decades older than any chatbot. To understand why an AI's opinion on a 5,000-year-old statue matters at all, you have to go back to the 1990s, when a Boston University geologist named Robert Schoch stood at the base of the Sphinx enclosure and noticed something that didn't fit the accepted timeline. The trench walls surrounding the Sphinx, the deep channel cut into the bedrock when the statue was carved, showed vertical, rolling, wave-like grooves running down the limestone. Schoch, working alongside independent Egyptologist John Anthony West, argued that this kind of erosion pattern is the signature of prolonged, heavy rainfall, not of thousands of years of dry desert wind. Wind erosion, Schoch pointed out, tends to cut horizontally and wears surfaces unevenly, scouring softer layers faster than harder ones and leaving a stepped, uneven profile. What he saw on the Sphinx enclosure walls looked instead like something water had carved from the top down, over a very long stretch of time. The problem was timing. Egypt's Giza Plateau has not seen the kind of sustained rainfall Schoch was describing for thousands of years, not since the end of what climatologists call the African humid period, when much of what is now the Sahara was a green savanna dotted with lakes and rivers. That wetter climate is not folklore. It is well documented in sediment cores, in fossil pollen records, and in ancient riverbeds that still lie buried beneath the sand. But that period ended roughly 5,000 to 6,000 years before Khafre is believed to have ruled, meaning that if Schoch was right about the cause of the erosion, the Sphinx would have to be old enough to have stood through that wetter climate, thousands of years earlier than mainstream Egyptology allows. For 30 years, this idea sat at the edge of academic respectability. Most Egyptologists rejected it, arguing that other explanations for the grooves, including chemical weathering, salt crystallization, or even simple weathering from occasional flash floods within the accepted timeline, could account for what Schoch was seeing, without requiring a radical new date. Schoch and his supporters pushed back, refining their measurements and pointing to comparable rainfall-carved formations elsewhere in the world. The two camps talked past each other for decades. Neither side produced anything that fully convinced the other. That stalemate is, in many ways, the real story here, not a single lucky guess by an algorithm, but a genuine, long-running dispute that never found closure. Which is why, when researchers began compiling a comprehensive dataset on the Sphinx, high-resolution laser scans of the trench walls, decades of erosion surveys, reconstructed ancient rainfall models for North Africa, published studies on how limestone weathers under different conditions, and records from ground-penetrating radar and seismic work beneath the plateau, feeding that entire archive into an AI model designed to search for statistical patterns wasn't as strange an idea as it might first sound. An algorithm has no career built on one side of the debate. It isn't chasing tenure, and it doesn't need a headline. It only has the data in front of it. According to accounts of the analysis, Grok was not told which theory was correct. It was simply asked to compare the groove patterns on the Sphinx enclosure against 3 categories of natural erosion: wind and wind-blown sand, chemical and salt weathering, and sustained rainfall, using the shape, depth, spacing, and orientation of the grooves as its variables. The result, as reported, favored the rainfall explanation by a wide statistical margin, with the wind and salt models showing weaker correlations to the observed groove geometry. The AI reportedly went a step further, estimating how long that kind of erosion would take to reach the depth seen in the trench walls, and concluding that it would have required rainfall sustained over centuries, not decades, and certainly not a handful of unusual storms within the accepted timeframe. None of this proves the older date. It's important to say that plainly. What it does is lend new, data-driven weight to a hypothesis that has existed in the scientific literature since at least 1992, when Schoch first published his findings and presented them at a meeting of the Geological Society of America. The AI didn't invent the theory. It stress-tested it against a mountain of information no single human researcher could hold in their head at once, and the pattern held up. From the erosion question, the analysis moved somewhere almost nobody expects it to go: the Sphinx's head. Stand in front of the monument, or even just look at a well-lit photograph, and something feels slightly off before you can quite name it. The body is immense, over 70 meters long, more than 20 meters tall, while the head appears noticeably undersized relative to that body, almost as if it belongs to a smaller figure entirely. Tour guides have offered this up as an artistic quirk for generations. But when the proportions were run through comparative analysis, the mismatch turned out to be more pronounced than simple artistic license would typically produce. This is where an older and equally controversial idea resurfaces: the recarving hypothesis. Some researchers, going back to comments made by Schoch and others in the 1990s, have proposed that the head we see today may not be the head the Sphinx originally had. Stone can be carved smaller, it cannot be carved larger. If the original head, potentially a full lion's head, matching the body, became eroded, damaged, or symbolically outdated over a very long span of time, a later dynasty could have resized and reshaped it into a more human, pharaonic face, quite possibly to associate the ancient monument with a living or recent ruler. It's a compelling engineering argument, and it isn't new. What is new is that the weathering patterns on the head and neck, when compared directly to the weathering on the body, reportedly tell two different stories: the body showing signs consistent with long-term water exposure, and the head and neck showing patterns more consistent with drier, wind-driven erosion, as though the two surfaces spent different lengths of time exposed to different climates. If that reading is accurate, it would mean the monument as we see it today is a composite, an ancient body, reshaped at its crown sometime later to reflect the identity of a king who may have simply been restoring, rather than originally creating, a far older figure. That would also explain something that has puzzled visitors for a long time: why a monument so precisely and confidently carved from bedrock has a head that looks almost like an afterthought bolted onto a body built on a completely different scale. Once the analysis turned toward the sky, the story picked up an entirely different kind of evidence. It is not disputed that the Sphinx faces due east, precisely toward the point on the horizon where the sun rises during the spring equinox. What is disputed is whether that alignment was meant to mark a single moment in history. Earth's axis doesn't just spin, it slowly wobbles, a movement astronomers call precession, completing one full cycle roughly every 26,000 years. Because of this wobble, the constellation that appears to rise with the sun on the equinox shifts gradually over millennia, moving through what astrologers call the Great Zodiacal Ages. Running a reverse simulation of the night sky, the analysis reportedly found that the constellation Leo, the lion, sat on the eastern horizon at the spring equinox sometime between roughly 10,500 and 8,000 BCE. If the Sphinx already existed in that window, and if its original form really was a full lion, then twice a year, at dawn on the equinox, a lion carved from stone would have faced a lion rising in the stars. Researchers who favor this reading call it, evocatively, lion watching lion. It's the kind of coincidence that either means everything or means nothing, and mainstream Egyptologists have been quick to note that alignment alone, however striking, is not proof of construction date. A structure can be built at one time and still happen to face a meaningful direction. Intention is very hard to prove after 12,000 years. Even astronomers who find the correlation mathematically interesting have been careful to say that archaeology, geology, and astronomy all need to agree before a claim like this can stand on its own. From the stars, the investigation returned to the ground, literally beneath it. For decades, surveys using ground-penetrating radar and seismic refraction around the Giza Plateau have picked up anomalies beneath the surface, including reports of cavities that don't match the pattern of natural fractures in the bedrock. Some of the most discussed readings point to a possible void beneath the Sphinx's front paws. None of this has been excavated or confirmed through direct archaeological access, and Egyptian antiquities authorities have historically been cautious, and at times resistant, to further invasive investigation of the site. What the AI analysis reportedly did was overlay the geometry of these unconfirmed subsurface features against the equinox sunrise alignment, finding a directional relationship worth flagging, while explicitly noting, in the reported output, that a pattern is not the same thing as physical proof. The investigation then widened its lens far beyond Giza, comparing construction techniques, stone-fitting precision, and geometric alignments across other ancient sites associated with astronomical orientation, a comparison in the same spirit as work popularized by writers like Graham Hancock, whose books have spent years arguing for overlooked connections between ancient monumental architecture around the world. The AI's comparative analysis reportedly surfaced a genuinely uncomfortable pattern. Some of the oldest stonework examined showed tighter joints and more precise alignment than structures built centuries or even 1,000 years later in the same region. If that observation holds up under scrutiny, it suggests something that runs against our instinctive assumption that technology only ever moves forward. It raises the possibility that some early construction knowledge wasn't refined over time, it was lost, and later builders worked from imitation rather than full understanding, copying the outward form of older monuments without possessing the original engineering behind them. It's worth pausing here to talk about how the scientific community actually responded once word of this analysis began circulating, because the reaction was far more layered than a simple yes or no. A number of geologists who have followed Robert Schoch's work for years said, publicly, that having a large-scale statistical model corroborate the rainfall-erosion pattern was interesting, but not something that should be mistaken for independent confirmation. The AI, after all, was trained on and fed the same body of published research the original debate was built from, meaning it was refining an existing argument rather than generating a new one from scratch. Several Egyptologists went further, pointing out that erosion modeling, however sophisticated, still can't account for localized flooding events, ancient repair work, or surface treatments applied to the stone across thousands of years of restoration attempts, any of which could distort the picture an algorithm sees. Others were more open to the exercise, noting that machine pattern recognition has already proven useful in fields like seismology and climate science, where the volume of data has long outpaced what a human team can manually cross-reference, and that there's no obvious reason archaeology should be exempt from that kind of assistance. What almost everyone agreed on, whichever side of the debate they sat on, was that no AI model, however capable, replaces the physical work of excavation, radiometric dating, and peer review. A statistical correlation is a place to start looking harder, not a place to stop. That caution becomes especially important once you consider how selectively the underlying data can be interpreted. The seismic anomalies beneath the Sphinx's paws, for instance, have been reported on since at least the 1990s, when Japanese researchers from Waseda University first conducted electromagnetic and seismic surveys on the plateau and noted subsurface irregularities. Egyptian authorities at the time neither confirmed nor pursued excavation of those findings, and the anomalies have sat unexplained in the literature ever since, not because nobody was curious, but because access to excavate directly beneath a protected national monument is, understandably, tightly restricted. When new data like this gets folded into a machine learning model decades later, it inherits both the value and the uncertainty of the original survey. It cannot resolve an ambiguity that fieldwork alone never resolved. The comparison to other ancient sites deserves the same careful treatment. When the analysis pointed to shared geometric or astronomical patterns among structures separated by oceans and thousands of years, sites like Göbekli Tepe in southeastern Turkey, dated to roughly 9,600 BCE and recognized as one of the oldest known monumental structures on Earth, or the precise solar alignments found at Stonehenge and at various Mesoamerican pyramid complexes, it wasn't claiming these cultures were in contact with one another, or that a single lost civilization built them all. Mainstream archaeologists studying Göbekli Tepe, including the late Klaus Schmidt, who led its excavation for decades, have generally attributed its sophistication to independent human ingenuity among early hunter-gatherer societies, not to some vanished predecessor culture. The willingness of separate, unconnected human groups to track the sun, the stars, and the seasons with remarkable precision may simply reflect a shared and very old human instinct. Watching the sky has always mattered to people trying to survive it, rather than evidence of one another's existence. That's a less dramatic explanation than a lost global civilization, but it is, on the current evidence, the far more defensible one. All of this circles back to one moment in Earth's actual, well-documented history. The end of the last ice age, roughly 12,000 years ago. This is not speculation. Massive ice sheets melted rapidly during this period, sea levels rose by well over 100 meters over several thousand years, and climates shifted dramatically across entire continents, a process geologists have reconstructed through ice cores, sediment layers, and coastal geology. It was, without question, one of the most violent environmental transitions our planet has experienced in the last 100,000 years. What remains purely hypothetical is the idea that an advanced human civilization existed before or during that transition, and had its physical traces largely erased by the very flooding and climate upheaval the geological record confirms did happen. No accepted archaeological find has ever produced solid evidence of such a civilization. It remains, at best, an open question rather than an established fact, and it's important that a story like this one treats it that way, rather than presenting speculation as settled history. So where does that leave us? The viewer, the skeptic, the curious mind turning this over on a screen. It leaves us roughly where honest science usually does, with a stronger question, not a final answer. The AI in this story did not excavate anything. It didn't uncover a hidden inscription or find a lost chamber. What it did was take an enormous, previously scattered body of real data, decades of geological surveys, climate reconstructions, laser scans, and comparative erosion studies, and search it for a pattern with a consistency that no single human researcher, working alone, could easily replicate. That is a genuinely useful thing for a machine to do. It is not the same as discovering the truth. The mainstream position, held by the great majority of Egyptologists today, still places the Sphinx firmly in the reign of Khafre, roughly 2500 BCE, carved as a guardian for his pyramid complex, its face representing royal power rather than a message from a lost world. That position isn't stubborn tradition for its own sake, it rests on architectural continuity with the rest of the Giza complex, on stylistic parallels with other Old Kingdom monuments, and on the simple fact that no rival civilization has ever been physically located in the archaeological record. The rainwater erosion theory, the recarved head, the age of Leo alignment, the deeper connections to other ancient sites, these remain open, actively debated ideas, not proven history, and honest researchers on both sides would tell you the same thing. What this story really offers isn't a verdict. It's a reminder of how science is actually supposed to work. A claim gets made, it gets tested against evidence, uncomfortable data doesn't get dismissed just because it's inconvenient, and conclusions stay open until the evidence closes them. Maybe the Sphinx really is exactly what the pyramids beside